Now, in terms of rates of reactions, guys, if we can just quickly remember what we went through, or rather what we discussed the last time, right? Is that the rate of a reaction is the speed at which a reaction is occurring. Now, if we're talking about a speed, we also need to know the definition, by the way. The speed at which a reaction is occurring. Okay, is the speed at which a reaction is occurring, which means how fast are the products being formed, or how fast are the reactants being used up. Now, there are many ways of measuring the rate of a reaction. You can measure the rate of a reaction by collecting the gas that is produced. So you can measure by collecting the gas, which means if you have your cylinder there, the gas would be here. You would have a syringe, right? And then in that syringe, you'd be collecting the gas that is being produced. So that means you'll be focusing on the product, and your graph is gonna be like this. Because as time proceeds, the volume of the gas is gonna be increasing. Okay, so this is the graph that you're gonna be working with. And if you're calculating the rate, you just look at 2 points, and then you're gonna say change in y over change in x. That's gonna give you the rate of the reaction. If they ask you for the instantaneous rate, sometimes they can ask for the instantaneous rate. If they ask you for this one, what you need to do is to draw a tangent on one point. You draw a tangent there, then you look at that point, right? Check the time, check the volume. That's the volume you're gonna write here, volume over, meaning you're gonna have y over x. That's gonna give you instantaneous rate, okay? But essentially you're just collecting the gas that is being produced, and that gives you a picture of how fast is the gas being produced, or how fast is the reaction going, right? Now, another way you can measure the rate of the reaction is to take the container, right? And then on that container, instead of collecting the gas, you can measure the amount of gas that is being produced. So you can measure the mass loss, So you put this on a mass balance, right? You measure the mass, okay? So the graph that you're gonna have there, remember the cotton wool that is usually put there. That cotton wool is to only allow the gas to escape, okay? It's to only allow the gas to escape, because we need to know how much are the contents that we have left. So that's why we only allow the gas to escape. Now, that mass balance, right, it's gonna give us the grams of the contents inside the beaker, okay? And then those contents tell us that how much of the reactants do we have left. Now the graph that you're gonna have there is gonna be like this: mass loss over time. Now your graph is also gonna be like this. But one can ask, why is the graph like this? Because if the graph is having this shape, logically, if you were to explain it, it means at T0 there is no volume of gas. But as time proceeds, there is more and more volume of gas that is being produced, until the volume of gas that is being produced is constant, which tells us that the reaction is complete. You see? So even here, we are still saying there is more and more as time proceeds. What are we saying? We are actually saying that as time proceeds, more and more mass is being lost. That's why the graph is like this. More and more mass is being lost. You understand? Until we no longer have mass being lost here, whereby here now when it's constant, we say the reaction is complete. Okay? So there we say the reaction is complete. Yes, so please, so remember, as a nice illustration, right, of how we collect the gas. Remember, as the gas is collecting inside here, what happens that the syringe is being pushed, right? And as that syringe is being pushed to that side, right, the gas is going to be pushing the syringe over time. So usually when you have your graph here, you're going to have volume of gas, and then you're going to have time. We know that at 0, let's just say seconds, we know at 0 seconds there won't be any volume of gas there because the reaction has not started. But after maybe 5 seconds, you find that the volume of gas that is collected in the syringe is around 10 centimeter cubed. And then maybe after 10 seconds, you find that it is now 12, right? Like that. Using these values of volume and time, that is why we end up having this graph. That's why we end up having this graph there. Okay, and what is important about this graph is to know that at the start here, at the start of a reaction, the gradient is the steepest, which means that is where the reaction is the fastest. That's very important, that when that part there, it's when the reaction is the fastest. And then as it proceeds, the reaction, the gradient decreases with time, which means the gradient now becomes more gentle, so the reaction is slowing down. So this is fastest here, fastest, and then it's now slower, slowest, and then here it's no more increasing. The volume of gas is no more what? The volume of gas is no more increasing. It is stuck at one point. If it is 20 here, it is stuck at 20 centimeter cubed. Why is it stuck there? This is because now the reaction has stopped. The reactants have been used up. Okay, the reactants, one of the reactants has been used up. One of the reactants has been used up, which means that the reaction is complete. Okay, the reaction is complete at this part here. All right, so no more gas is being produced. But when it starts, it is the fastest, and then it becomes slower and slower and slower, right? So this is why they try to explain here, guys. This is the Siavula book, like I said, right? If you go to it there, you'll find this information. It's a free textbook online there. And then if you do not have it, I'll also just try to share it with you guys. Now, usually, since the gas is collecting inside the syringe, you might want to test whether really is that gas, what type of gas is there. Usually you can be collecting hydrogen gas, or you can be collecting carbon dioxide gas. Guys, actually, you see these reactions that you are seeing here. Please know that these reactions that you are seeing here, these reactions are called gas forming reactions. Okay, these are called what? Gas forming reactions. And usually gas forming reactions are the type of reactions whereby you can collect the gas. So the common ones is magnesium plus hydrogen sulfate, which is an acid. So you have a metal, right? You have a metal plus an acid. What does it produce? It produces a salt plus hydrogen. Okay, that's why you see this is your salt here, and then this is your hydrogen gas. So these are called gas forming reactions, which means gases that form which means reactions that form a gas as a product, right? And then another example that they like a lot is this one. Okay, it's this one here. And then on this now, you also form a what? Here you have a metal carbonate. Metal carbonate plus an acid. what you produce is a salt plus water plus carbon dioxide. Because you have a metal carbonate, you form salt plus water plus carbon dioxide. And you can see this is your salt here, this is your water, and then this is your carbon dioxide here. Okay, so it's a very common reaction that they like to put in the exams, so just take note of it. And then we have lastly the reactions that produce oxygen, right? And those reactions that produce oxygen, which one is it? This is the one here whereby you have hydrogen peroxide, which decomposes to form water and oxygen. Okay, so when they give you reactions, especially where they are collecting the gas, it will be one of these three. Okay, it will be one of these three. So just watch out for that. Okay, I hope that we understand how we can measure the rate of a reaction by collecting the gas. Think of you as being in the laboratory there. You have your syringe, you have the glass, you have the cylinder, right? Where the reaction is taking place inside there, inside here, and then when you collect the gas that is being produced there. Right, so that is exactly what is going on there. Now another way, remember another way of measuring a rate of a reaction is whereby we take the beaker. Now that beaker, we put a paper, and then on that paper what do we draw? We draw an X. So that beaker will be, my beaker is very ugly, but you will see a nice one there, right? Let me show you a nice, because my drawings, guys, they will throw you off shame, but this one you will actually see that it's more beautiful, isn't it? Just beautiful. So what is happening here, right, is that we're trying to measure the rate of a reaction by looking at the amount of precipitate that was formed. What is a precipitate? This is simply a solid that is being produced as a product. Here's the solid here. Do you see that this is the only solid? This is in aqueous, this is aqueous, this is liquid, which means all these here, it's liquid. Then this is the only solid that is being produced as a product. Okay, so this reaction of sodium thiosulfate, I told you guys that this is the reaction, they like it a lot, and this is the only reaction that we have whereby we are producing a precipitate. If they show you another type of reaction whereby they are not using sodium thiosulfate, that is still okay. When you just have to check whether you produced a solid as a as a product, right? As long as you produced a solid as a product, that becomes your precipitate there. Precipitate. Okay, and whenever you are dealing with the precipitate, remember that's when you take a flask and then you draw an X on the paper. Now the thing is, when you are looking at that flask, right, when you are looking at that flask, remember you are in the lab. As more precipitate is being formed, right, as the precipitate is being formed here, it blocks the view of the X. That's why here you find that it's now like this, which means that the view of X has been blocked by the precipitate that is being formed. And the precipitate is a solid. So because it's a solid, it blocks the view because you're looking from above. It blocks your view of the X that is below. Okay? So that is what we call a precipitate type reaction, whereby you are forming a precipitate. If you form a gas, you collect the gas in a syringe. If you form a precipitate, you take a paper, you draw X on it. As the precipitate is being formed, it blocks your view. In that way, you can measure the rate of the reaction. So that's what they're trying to say. As the precipitate forms, less of it can be seen, referring to the x. Less of the x can be seen. Okay, so this one usually you can't have a graph. But well, sometimes you can just try to draw the graph, but it's difficult to draw a graph because what will be on your y-axis and x? I understand here is the time, but what will be here? Because you are not measuring anything. Are you measuring the volume of the precipitate? No. Are you measuring the mass of the precipitate that is being formed? No. How can you measure the mass when you don't have a mass balance? You understand me? So it's difficult to have a graph for this reaction. That's why we don't really include a graph for it. Okay? However, you will be presented with this. Okay? You will be presented with this type of, type of graph, whereby instead of them measuring the amount of precipitate, they look at the volume of the water in the beaker. They look at the volume of the water. You see? Yeah. Then perhaps you can then have what? Your graph. And here's what is then important there. When you represent your results on a graph, concentration will be on the x-axis and the reaction rate will be on the y-axis, right? So this is because the original volume of the sodium thiosulfate can be used as a measure of concentration. So what they do is that they take the original volume of this sodium thiosulfate, the original one, the one you start with, they take it, right, in the original volume there. They take it as the initial concentration. And then as time is going, right, as time is going, what is happening? You can see that the volume is decreasing. This is the volume of the sodium thiosulfate, of the Na2S2O3. That is the volume there. So what is happening is that as time is increasing, right, the volume of sodium thiosulfate is decreasing. Forming what? Forming the precipitate there as a product. But one can ask, why is the volume of sodium thiosulfate, which is this part, why is the volume decreasing? This is because the reactants, naturally their concentration should decrease because they're the ones that are forming the what? The products. So the concentration of the reactants is going to decrease. So that is why you see that the volume is decreasing of sodium thiosulfate, because it is forming the products. It's forming the precipitate. Okay. So when they measure the reaction rate, this is the formula that they usually use, 1/time. Okay, that will be what they use there, but it's just essentially the amount of product that is formed over the reaction time, right? Because the product is the precipitate. All right, so that is it there. That is it. So just understand, guys, that what we are trying to do here is to measure how fast are the products being formed. Now, how fast this solute or this precipitate, how fast it's blocking our view here, tells us about how fast the reaction is. Okay, that is as simple as that. And then we also have reactions whereby there is change in color. We can measure the rate by using the change in color to say if we have, let's say, ethanoic acid reacting with sodium hydroxide, right, and we titrate them. These are like acid-base reactions, right? What happens there is that you will see that as you are titrating them, there will be a change in color, right? So that change in color will tell you about how fast the reaction is. All right, So the faster the color change, the faster will be the reaction rate. Okay, but this one, hardly we see graphs there. Hardly we see graphs. The ones that are important in terms of graphs, I think I mentioned that is this one whereby you are collecting the gas. Okay, these gas forming reactions, they are quite important in terms of their graph. Okay, but usually for the precipitate and for this color change, we don't really get a lot of graphs. Now, we also said we can measure the change in mass, right? Which means we are looking at the mass loss. Okay, now the mass loss, here it is there. You can look at it in two ways. Remember the cotton wool, we said it only allows gas to escape and not the liquid, meaning not the contents inside. And now, if you get this graph, if you get a graph like this, what you are saying is that as time is proceeding, the amount of mass that you have here is decreasing. You see that here we're starting with 103.2 on your mass balance. After maybe 2 minutes, it will be maybe 80 grams. After another 2 minutes, maybe it's 60 grams. You see, it's decreasing. That's why you get a graph that is like this. This is because the amount of reactants in your glass beaker there, or in your vessel, right? The amount of reactants is decreasing because the reactants form the product. Now you can also think about it in this way. This is if you said your y-axis is mass, the mass of these things that are inside. But if you say your y-axis is the mass loss, if you are saying is the mass loss now, you are saying how much is being lost per unit time. You are saying you're going to start with 0 seconds as your time. And then here you're going to have mass loss. You're going to have mass loss. You have not lost anything. But maybe after 10 seconds, you have lost 2 grams that were here. Because if it move from 103.2 to 80 grams, it means you lost how much? You lost around 23.2. You see, so here you'd write 23.2. Then after another 10 seconds, which is now you say maybe 20, you check now to move from there to there. How much did you lose? You lost another 20 grams, like that. So the amount of the mass loss is increasing. The amount of material you are losing is increasing. That's why your graph looks like this. Okay, so that is the interpretation. The interpretation is that here my contents, the amount of things I have in my beaker, right, is decreasing, while here the amount of things I'm losing per unit time is increasing. I'm losing more and more and more. Here they are decreasing. The mass is decreasing of the things that are inside there. So those are the two graphs that you can expect for mass loss, right? Mass loss, and then the other one is just mass, the amount of reactants you have. Since the amount of reactants you have is decreasing over time, that's why the graph will be like this. And then here you're looking at the mass loss, how much has been lost. You're losing more and more and more per unit time. That's why the graph is like this. Okay, I hope that is clear then. So that is how to understand that. Okay, so in a nutshell, so as a summary of what we're talking about in terms of how you measure the rate, so we know that we can measure the gas, we can collect the gas that is produced. This is particularly for gas forming reactions. Okay, this is for gas forming reactions. And then number 2, what can we do? We can also Oh, by the way, the gases that we can collect is like the likes of hydrogen, carbon dioxide, and oxygen. And then also we can check the precipitate formed, ne? Precipitate formed. This is where we take, our glass beaker, then we put an X there on the paper. There we put X there. So this one is for the precipitate forming reactions. Precipitate forming reactions. Okay, great. And then another thing we can also do, what can we also do? We can also measure the color change. We can measure the color change, whereby we're just looking at how fast the color is changing. This is for acid-base reactions, né? For acid-base reactions. If you ever see an acid and a base there, you can then conclude to say, for me to measure the rate of this reaction, I must measure the color change. Okay, and then lastly, we said we can measure the mass loss. Okay, mass loss. So this is whereby you can either this is for many reactions, but also it's for gas forming reactions. Are you aware that it's actually gas forming reactions? Why am I saying that for mass loss is gas forming reactions? Because how are we losing the mass? We are losing the mass because the gas is escaping that is being produced. You understand? So if I have, let me just give you this example. I know that if I have zinc, which is a metal, plus hydrochloric acid, what is going to happen here is that, so zinc is a solid, let's say the hydrochloric acid is in aqueous, we're going to form a salt and hydrogen because it's a metal and an acid. So you're going to form zinc chloride. You're going to form zinc chloride, which is also will be in aqueous, and then plus hydrogen gas. So now that we have that, so let's remember that if you decide to collect this gas, right? If you decide to collect this gas, then you are here, whereby you're collecting the gas. But then if you decide to measure the mass loss, to measure the reactants, then it means you are here on mass loss. You're gonna allow the gas to escape. Okay? So both these are very much connected. Both of them, they are related to gas forming reactions. Okay? Both of them. Then precipitate is the precipitate forming reactions. Color change is the acid-base reactions. Okay, so we're gonna do a massive walkthrough over these guys. Remember that reaction rates, right? Also they include this part, right? But we'll talk about it. I think it's just grade 11. We'll talk about it. The most important thing is this. Let's know the definition of rate. Let's know the definition of rate because it will always be there. Rate is the change in concentration of reactants or products per unit time. I think it's one of the simplest definitions ever. What are the factors that affect the rate? Remember, is the nature of a reactant, is the concentration, surface area, temperature, and catalyst. If you have a higher concentration, you have a faster rate. Greater surface area, faster rate. Higher temperature, faster rate. Catalyst, it increases the rate without undergoing permanent damage. Those are the factors we should know. How do we calculate the reaction rate? It depends on your graph and whether you're looking at products or reactants. This first part here is when you're looking at the product. Remember, graphs for products, I'm gonna draw it here just next to the products. Graph for products looks like this, guys. You should know that if you get a graph like this, you're mostly dealing with a product. So on the y-axis here, it could be volume, or it could be number of moles, or it could be concentration, or it could be mass. You see, that's why if it's concentration there, and then here it will always be time. If we're looking at the graph of the factor versus time. So if it's concentration, you will say change in concentration over time. If it's mass, you say change in mass over time. If it's volume, change in volume over time. If it's number of moles, change in number of moles over change in time. The graph for reactants, guys, is usually like this because the reactants are decreasing. So if it's concentration on the y-axis, you use negative now, but change in concentration over time. Just make sure that you put negative depending on what is on your y-axis there. So this is your y-axis there. Remember, your x-axis will be time. Okay, what is the unit of the rate? It is any unit of the above quantities per second, which means if I'm talking about concentration, right, the unit will be this. This is for concentration, because concentration is mole per decimeter cubed, right, and then over change in time, which is second. So it will be mole per decimeter cubed per second. If we're dealing with mass, it's going to be grams per second. If we're dealing with volume, it's going to be decimeter cubed per second. If we're dealing with moles, it's going to be mole per second. So the unit of rate depends on whether your y-axis is dealing with is the volume or the concentration or the number of moles or the mass. I hope that is clear. Right. Now, what is your independent variable? Your independent variable is going to be the factor. It's going to be the factor that is changed. That means your independent variable could be any of these. All of these are your independent variables. These are your independent variables. If I ask you, give me the independent variable, you check the factor that is being investigated. Okay. You check the factor that is being investigated. That is your independent. What is your dependent? It will always be the rate of the reaction. Okay? It's going to be the reaction rate. What is a controlled variable? If the independent variable, let's just say it's temperature, it means all the other factors, I must keep them constant. All the other factors become your controlled variables, such as surface area, such as concentration, nature of reactant, state of division, which is still surface area. Those things, you should keep them constant so that you are investigating one factor at a time. One factor at a time. And then what is an investigative question? Yo guys, I was marking your papers there that you sent. Your questions, guys. Remember, your question can start with how does, what is the relationship? What is the relationship between this and stuff? But your investigative question should always include the independent variable and the dependent variable. Which means, how do I phrase it? I will say, how does temperature affect the rate of a reaction? How does surface area affect the rate of a reaction? How does concentration affect the rate of a reaction? How does the nature of a reactant affect the rate of a reaction? You feel me? Or you can say, what is the relationship between temperature and the rate of a reaction? What is the relationship between concentration and the rate of a reaction? What is the relationship between number of moles and the rate of a reaction? As long as you are mentioning the independent variable and the dependent, that's where you'll get your 2 marks. Same thing with your hypothesis. Your hypothesis is a prediction, right? So the prediction could be when it must also include the independent and the dependent, or else it's not a complete hypothesis. Must also include this and include that. When you're predicting, you can say, you can start it with when. When temperature increase, the rate of a reaction is going to increase, and vice versa. Or when concentration increase, the rate of a reaction is also going to increase. So your hypothesis must have an independent and a dependent variable. I hope that is clear, guys. Then what is your conclusion? Your conclusion now is drawn after you've investigated. So your conclusion could be that, therefore, I can remember you had said on hypothesis, when temperature increases, the reaction rate will decrease. Your conclusion will also be that, but again, after you have investigated. Okay, so please, you should know how to get investigative question and hypothesis, especially in this topic, guys. We cannot do that. Please, please, please. Okay, so now this is just also a summary of what we've talked about already. Measuring the volume of gas, then we get this graph. Measuring mass loss, we did say that the contents in the flask are decreasing, that's why we have this. Or we can also have that graph as being like this, whereby we're saying we're losing more and more as the time proceeds. Alright, this is mass loss. We put a cotton wool to stop spray loss, but only gas can escape. And in precipitate, we talked about it, that we're talking about sodium thiosulfate, which reacts with hydrochloric acid to form a yellow precipitate of sulfur. So the time, how long it takes a certain amount of sulfur to form is measured, and the reaction is observed from the top. Okay, and viewing a black cross on the white paper, as you can see here. So the X is eventually obscured. I like this word. You will hear grade 9s when you are in front and then they're trying to write notes. But I say, you're obscuring my view. Hey, man. No, very good. The word obscured, right? Very fancy word for blocking the view, right? So it's the X eventually, its view is blocked by what? By the sulfur precipitate that is being formed. Okay, so that's what is happening. Then you can repeat it at different temperatures, right? If you are repeating it at different temperature, remember that is that is now what is called the factor that you are investigating. Okay, so it means you must keep, if you decide to change the temperature, you must keep the concentration the same, okay, to measure the effect of temperature on the rate, which means maybe you can do this at 20 degrees Celsius and then you change the temperature maybe to 50 and see how fast is the X going to disappear there from your view. And then if you can also do it with different concentration of the sodium thiosulfate. Maybe you can use a sodium thiosulfate of 0.2 mole per decimeter cubed, right? And then maybe use the one with maybe 0.8. And if you decide to do that, since you are changing concentration, you must keep temperature constant. So you must do it at the same temperature. That becomes your controlled variable. So controlled variable is the one that you keep constant. And then like we said before, this is also what they're trying to show you there visually. You see that initially you can see the X. As time is going, you can partially see it, and then after a long time, the cross is invincible. Then you can stop the watch, right? Then reaction rate, we said we calculate it as 1 over time. Okay, if this whole thing took 20 seconds, you just say 1 over 20 seconds. That gives you the rate. Okay, and then for the cross to become invincible, the same amount of precipitate is formed in each. Therefore, the mass of sulfur formed is the same and is represented by the 1. So why this reaction rate is like this is because if this takes 20 seconds and then you repeat the experiment, and then now for the second time, maybe you were doing it at 20 degrees Celsius, then maybe you change the temperature, now you're at 50 degrees Celsius, and then now it takes 10 seconds. You are still forming the same amount of sulfur. It's just that the time of forming the sulfur is different. That's why we use 1 over 20 here, and then here would say 1 over 10. Okay, that's what they are trying to explain there. So I hope that for sodium thiosulfate it's clear, guys. Okay, you can either change temperatures, you keep the concentration constant, or you can change the concentrations, you keep the temperature constant, to see how it affects them. Right, that is it there. Then we talked about the collision theory, right, to say for ineffective collisions, the particles must collide with sufficient energy and have correct orientation. Okay, this Boltzmann-Maxwell distribution curve, let's just also know that it is a curve that tells us, or rather that shows us the amount, the particles that are taking part in the reaction. Okay, but most probably it's nice to talk about this when we have talked about endothermic and exothermic. So let's just skip it for now. But otherwise, that's what we just be left with to finish this topic. These are the definitions we need to know. You should know also what is percentage yield. That is actual mass obtained over calculated mass times 100. Okay, and then percentage purity is mass of the pure sample over the total mass, but that one is for calculations. Okay, yeah. Now what I wanted to go to was here. Okay, this is where I was running to. Sorry to rush a bit. This is because I just wanted you to be confident in terms of reaction rates. In fact, the moment you see the question, you must already know what we are talking about. In this question, they said learners use the reaction between impure powdered calcium carbonate and excess hydrochloric acid. This is calcium carbonate. You are talking about a metal carbonate. It's a metal carbonate. What are we forming there? We are forming the salt, you are forming water, and you are forming what? CO2. Which means this is what type of reaction is this? It's a gas forming reaction. And since it's a gas forming, that means if I collect the gas, right, I can choose to collect the gas or measure the mass loss. Then you will look at this question and see what they were doing. They said they performed 4 experiments under different conditions, which are shown here. For experiment number 1, the concentration was 1 mole per decimeter cubed. The mass of the impure, this calcium carbonate is impure, Please know that it's impure. If something is impure, guys, I want you to understand that when we are saying something is impure, think of that calcium carbonate as a stone, or think of it as the egg yolk, the egg, Think of it as a boiled egg. I'm using quite an example, but yeah, think of it as a boiled egg. In a boiled egg, inside, what do you have? You have this yellow part, which is the yolk, Perfect. You have the boiled egg here, and then inside you have the yolk. If something is an impure substance, it means it's only the yolk that is going to take part in the reaction. The rest of the body, that whitish thing you see on the egg, that whitish thing is going to remain. Okay, it's going to remain. Only the yolk is going to take part in the reaction. That is what is called a impure substance, which means in the middle there you have calcium carbonate, but outside you have some other stuff which is not calcium carbonate. But what is going to react is only the calcium carbonate. That is an impure substance. Now they said they comparing the results of experiment 1 and 3. I want you to check experiment 1 and 3. I'm just going to zoom in on them. This is experiment 1, and then this is experiment 3 here. When you look at those two experiments, when you must check to see what was kept constant, what was changed. I want you to take a second to look at them. What was kept constant? What was changed? Can you type it for me there? So indeed, when you look at it, right, the concentration in experiment 1 was 1 mole per decimeter cubed. In experiment 3, it was also 1 mole per decimeter cubed. The mass of the impure calcium carbonate that was used was 15 grams, and in here it was also 15 grams. But the temperature was changed. For experiment 3, the temperature was 40. This one was 30. So this means that these three, right, or rather these two, become your controlled variables. Controlled variables. And then this one become your independent variable. Your independent variable. What is the dependent? Is always the rate of the reaction. So they say write down the independent. How nice. Is the what? Is the temperature. And then what is the dependent? Is the rate of the reaction. Please guys, do not look at the graph given here, right? And then you say, the dependent variable is the volume. No, dependent variable is always the rate of the reaction. And then now they say use the collision theory to explain why the rate in experiment 4 will be higher than in experiment 3. That's when you start telling them that, or they said experiment 4 and 3. So it means we're comparing 4 and 3. So 4 is this one. This is 4 here. Now, you also don't just compare. You check the factor that was changed. What was changed between experiment 3 and experiment 4? The concentration is the same. The mass is not the same. In experiment 4, they used 25 grams. Right, this one they used 15 grams. While the temperature was the same. So it tells you that your controlled variable is the concentration and the temperature, but your independent variable between 3 and 4, the independent is the mass. So when you explain using the collision theory, you tell them that in experiment 4, the mass was increased, or rather more mass was used. More mass was used, right? This increases chances. This increases chances of effective collisions per unit time. Effective collisions per unit time. Again, we're using the collision theory. You always have to include effective collisions per unit time, which increases the rate of the reaction. Or you can tell them that if you have more mass that is used, more particles will collide with correct orientation, more particles will collide with sufficient energy, therefore more effective collisions per unit time. I actually recommend you answer it that way. You tell them more particles will collide with correct orientation, more particles will collide with sufficient energy, and therefore there will be more effective collisions per unit time, which increases the rate of the reaction. Now they obtained the graph of ABCD from their results. Please remember that in experiment 1, 2, 3, and 4, we are still using the same reaction, this one. And since we are still using that reaction, it is still a gas forming reaction, which means in each experiment you are still collecting the gas. That's why you have 4 graphs here. It's all the graphs for collecting the gas. Do you see? Do you remember these curves? Okay. Then I think here they just wanted you to tell them which one is the highest in the likes. Well, if you can check, A is the highest. Please know that this one here will be the highest reaction rate. Okay, this will be the highest reaction rate because it is the steepest gradient compared to the rest. Okay, compared to the rest. So that is the one there, and then you just explain to them by comparing different experiments. You compare 2 and 3, you compare 1 and 2, and the likes. Okay. But maybe just before we go too deep into the calculations, and just look at the next one. What you have here is zinc, HCl, which is a metal and an acid. What did you form there? You formed a salt and a gas. So this is still a gas forming reaction, right? And you still have different experiments there, or what? And then those different experiments, they are still changing different different factors. But they told you that they use the same volume of hydrochloric acid and 1,2 grams of zinc in each of these 5 experiments. So the volume was constant, the mass was constant. So what was being changed? Look at experiment 1. This was the concentration, and then the temperature. They started with 20 degrees, and then they now use 34. So they changed the temperature. That tells you that that is the independent variable there. That is the factor that was changed. And then the state of division, they were using granules. Guys, when you talk about state of division, it refers to the solids. Your solids could be powder, or your solid could be granules. When you talk about granules or lumps, when you talk about them, just think of an uncrushed peel and a crushed peel. Granules, it means uncrushed. Powder means it's grinded, it's crushed. So what they did there is that they used a different they increased the temperature. So this is to see that if my temperature is 20 degrees Celsius, if this reaction, remember, it's going to be occurring inside of a beaker. So that beaker, you keep it at a temperature of 20 degrees Celsius for the first part, and then you change the temperature to 34, and then you look at the graph that you have. And for the first part, it's going to be a graph, and then you draw for the second part, you're going to have another graph. Then that tells you that since this was at 34 degrees Celsius, it means the reaction rate was higher when we increased temperature. What about experiment 2? They used this concentration, and then they also increased temperature, but now they used powder instead of granules. And what do you realize there is that the concentration was kept constant. They changed temperature, at the same time they also changed the state of division. They used granules, they also used powder. Look, when they used granules, it was 50. That was the time that was taken to complete the reaction. It was 50. Whereas when they used powder, the time that was taken is 10 seconds. So when was the reaction fastest? When they used powder, because it takes less time. If it takes less time, it means the reaction is fast. If it takes more time, it means the reaction is slow. Okay. Then, now, what did they do here? Now here they kept it as powder again. They still changed the temperature to the same thing. 35, 36 is more like the same thing. But instead of using 0,5 as the concentration of the acid, they now used 0,8. How much time was taken for the reaction? 6 seconds. That means the reaction was more faster. Why? Because the higher the concentration, the faster the rate of the reaction. You see, check experiment 4 and 5. Experiment 4 and 5, they use the same concentration, but now the temperature, they moved it from 35 to 50. Here they moved it from 20 to 34. And both of them, they were granules. Where is the reaction going to be faster? Exactly when the temperature was 50. That's why it took 8 seconds and here it took 11 seconds. Are we clear? Now, I want you to check 2.3. They say, the learners, they compared the results of experiment 1 and 3 to draw a conclusion regarding the effect of concentration on rate. Give a reason why this is not a fair comparison. Now, where is experiment 1? Here it is here. And then experiment 3 is here. Experiment 1, they used 0.5. Experiment 3, they used 0.8. Now it's becoming a bit messy, so sorry. Let me just do this. Let's just focus on the ones that they want. Né? So this one they used 0.5 and then this one they used 0.8. So they changed the concentration. Right. Now they used a temperature now of 34. And then from 20 to 34, they changed the temperature. They used 20, and then after that, they used 34. Here, they used 20, and then they used 36. And then here, it was granules, and then here, it was powder. Why is this not a fair comparison? Think about it. Why is it not fair to compare those two experiments? It is an unfair comparison because they changed so many factors. They changed concentration, they changed the state of division. They used granules and then here they used powder. If you do that, you are messing up your head now. You won't know what really affected the rate. Is it that this zinc, that was the solid, right? Is it that it was powder instead of granules? That's why it took 6 seconds. Or is it that it had a higher concentration? That's why it took 6 seconds. That's why it was faster. So if you changed two factors at the same time, your result, your experiment is not going to be regarded as a fair comparison or as a fair experiment. No, let's call it comparison because you already did the experiments. So if you change different factors, you compare experiments whereby many factors were changed, that won't be a fair comparison. You must only change one factor so that you can then know what caused the change in the rate of the reaction. I repeat it again. You must change only one factor so that you understand or know what caused the change in the rate of the reaction. If you change two factors or more, we won't know what changed there, what caused the rate to be higher or lower. But I hope that is clear. Right, here's another question here. You see here what they did. They used magnesium, a metal, acid, formed hydrogen. Already you know that this is a gas forming reaction. That is why you have the graph here like this. You're collecting the gas. Okay, you're collecting the gas. And T and S means you actually did maybe 2 experiments there, but I just want to quickly run through so that you check. And then here, what did they use? They used diluted acid, right, which is reacting with a zinc. So it's still a metal and an acid. You are going to form, it's a gas forming reaction. Gas forming. And because you're going to produce a gas, that's why your graph is like this. You see? Next one. What did they use here? They used methanol and hydrochloric acid. Then they formed this and water. Now this is quite different from the reactions we had. Let's actually go through it. They saying, but methanol, okay, state 2 factors that can increase the rate of this reaction. Looking at this reaction here, what would be 2 factors that can increase the rate? Well, what could we talk about? Perhaps we can talk about the concentration, because we're talking about aqueous solution there. So we can say concentration, right? We can also say temperature, but we can't say surface area because there is no solid here. Surface area and state of division, they only apply to solids. Can we say catalyst? Yeah, we can also maybe add a catalyst. It can affect the rate of the reaction. Yeah. Is there anything else I'm leaving out? Nature of reactant? Well, rarely. Now, define the term reaction rate, you know the definition. Then this is what they came up with, right? They measured the concentration of HCl at different times. So let's see what is happening. From T0 to 215, the concentration of HCl, which is your reactant, usually should it increase or decrease? It should decrease because it's a reactant. That's why you see that it's decreasing here. So because they are focusing on the reactant, when you draw the graph, it's going to look like this, whereby here it's going to be concentration of your HCl, and then here it's going to be time. So they were investigating the factor of concentration. Then they say calculate the average reaction rate in mole per decimeter cubed during the first 15 minutes. Now this is what we need to know now. I'm gonna say into this document, it has answers there, guys, but it only gives you the final answer. So when you must see or how do you get to that answer. So when you calculate rate there, since we're talking about concentration and it's a reactant, it's important to know that it's a reactant. So you're gonna say minus change in concentration over change in time. Then you say minus. They said during the first 15 minutes. So I have to look from 0 to 15. My change in concentration was 1,45 minus 1,90. So that's what you would write. 1,45 minus 1,90. You divide by 15 minus 0. Then you get your answer. But your answer is going to be in mole per decimeter cubed per minute. And if we do that calculation, I'm quickly going to do it here. Let's say here it's 1,90, right, minus 1,45. The answer becomes 0,45. If you divide it by 15, because they said per minute, divide by 15, you get 0,03. Exactly the answer there. So indeed, this is 0,03 mole per decimeter cubed per minute. I'm saying per minute because they wanted it in per minute. If they wanted it in per second, I would have to change that minutes to seconds. So it's important to know the unit. So I just wanted to see that and how you do that. Okay. Then you see here they said use collision theory to explain why the reaction rate decreased. What was the factor? Concentration. If the concentration is decreasing, what is going to happen? Less particles are going to collide with correct orientation. Less particles are going to collide with sufficient energy. Less effective collisions per unit time. And therefore the reaction rate is going to decrease. You feel me? Right. These stoichiometric questions, right? We still have to do them, guys. You know, it's stoichiometry, a lot of stoichiometry there. Now, this one here, sodium thiosulfate. Ne? Remember we talked about sodium thiosulfate, so already you know we're dealing with the cross, obscuring the view of the cross. Now they did 4 experiments, A to D, and on those experiments, now check, they looked at the volume of the sodium thiosulfate. Here it was 25, and in the volume of the water it was 0. Why was it 0? Because when you start there, you only have this and that, you don't have water, so it's still 0. But as time proceeds, remember now you are measuring the time it takes for the cross to disappear. The cross disappeared after 50 seconds. The cross disappeared after 50 seconds. What was the volume of HCl when the cross disappeared now? The volume of HCl when the cross disappeared was 5. Oh, sorry, this is the volume that was used for HCl. It was 5, so they kept it as 5. They didn't change the amount of acid they are using for all the experiments. What they were changing is the amount of sodium thiosulfate, that is the one that was being changed. Oh, and do you see actually this 0 here, guys, it means after 50 seconds the cross had disappeared. However, there was 0 liters or 0 centimeter cubed of water that was formed. Let's see, in experiment in B, they used 20, and then after 62.5, the cross disappeared, but then the volume of HCl of water, of this water that was produced, it was 5 centimeter cubed. Here they used 15. And then after 83.3, you see it takes more time to disappear. And then the volume of H2O that was produced, it was 10. Here they used 10, and then it took 125. So that means the lesser the volume of sodium thiosulfate, the more time it takes for the cross to disappear. So they say state 2 factors that can influence the rate of this reaction above. What could be the 2 factors? The concentration of HCl. The concentration of this HCl can affect the rate, right? Because you can find that maybe the high concentration of HCl is the one that is causing this, to take time to disappear. Okay, just that the volume, they kept it constant, but concentration can affect. What else? Surface area? No, not surface area. Temperature? Definitely, temperature can affect. So you can name those 2. Write down the name or formula of the product that causes the cross to become invincible. What causes this thing to disappear is the precipitate. And what is your precipitate? Is this solid substance, the sulfur. So here you just tell them that is the sulfur. S. Give a reason why water is added to the reaction mixture in experiment B to D. So here they were adding water from B to D. Why is it added to the reaction mixture? Oh, you see now this thing of not reading the instructions. Yeah, but why are we adding water? Maybe why would you add water there? Oh, guys, is there anyone who can see why they're adding water? So check. Here they didn't add water, but at each experiment, as you go down, they're adding more and more water to the reaction mixture. and then measuring the time it takes for the cross to disappear. So why are they adding water? Is there anyone who can, and I think in 6.1 it's a giveaway on why they add water. Guys, they're adding water so that they can decrease the concentration of HCl. You see this HCl, how else will you decrease its concentration? Is if you add water. Okay, so they're adding water to decrease the concentration there. Investigative question: how does concentration affect the rate of a reaction? You see. So, yeah, I think, guys, you understand how to approach these questions. Please, and I'm hoping that when you see things like this, immediately say, oh, it's a gas forming, there's a mass balance. Oh, then I know that I'm measuring the mass loss. So in each question that you're gonna look at, right, for now it's not gonna be something that is new to you. You should understand immediately and be able to interpret, but you need to do a lot of questions. Yeah, so you need to just do a lot more. You see, even here it's still a gas forming reaction, but they're using mass balance. So if the graph is decreasing like this, it tells us that they're looking at the amount of something that is decreasing as the gas is escaping. So they looked at magnesium. Experiment 1, experiment 2. Experiment 1, they used a certain mass of magnesium ribbon. In experiment 2, they used magnesium powder. What is that? State of division. State of division, which is like your surface area. If you use a powder, and here they use the powder, and in here it was a ribbon. And I want you to check experiment 2. Do you see that experiment 2 is at the bottom? This is your fastest experiment because they used powder, while this one is slower. If your graphs are decreasing, the fastest will be at the bottom. But if your graphs are increasing, your fastest will be at the top. Just remember that. Okay? Then they are looking independent, how controlled. Independent, you know that it will be the surface area, because that is the one that they changed. But controlled will be the other factors like temperature, you must keep it constant, concentration, you must keep it constant. Yeah, you see, you can name those. Check, guys, they're still using, this one is what? Zinc, that gas forming reaction. We did something like this before. They repeated, it was in 2018. Now, you'll also have graphs whereby they take the reaction rate itself, the dependent, and then remember, Kiro, we're saying the factors are the independent, so they actually put the independent there, like they take the factor itself and compare it with the rate. So if you get a graph like this, you know that means the higher the concentration, the higher the rate of the reaction. You see, they're just directly comparing the factor with the reaction rate. Okay. No, this is just a repetition. So please, guys, practice a lot of previous papers, right? And then see how you are getting it. If you're facing troubles, please just contact me. Say, I was doing this one, I don't understand it. But we still need a time whereby we're gonna look at the calculations themselves, especially for percentage purity and the likes. Trust me, we are still gonna look at them. I will keep that in mind, but then keep practicing to push. Yeah, boy.